All right, so as I mentioned before, not much is changing on this on the schedule here, but I did want to just follow up with the midterm. I moved it to week 7, which so it makes the most sense to do it on Tuesday, which then means either we have exam in lecture and then nothing for lab, or just do a lab that's unrelated or something, or we do the midterm during the lab time and make the morning our review session. It's not quite as good as doing a review on a different day, but it still gives us time to ask questions and then take a break before we take the test. So when we get closer, we can decide what we want to do with that. I'm open to either doing the midterm in the morning and then having a light paper lab homework assignment sort of thing.
Oh,
That's true. Well, so it could either be from 10 to noon, double for you, or it could be from 1 to 3, double for you. So you would go to 5. Either way, it just depends on whether you feel like you take tests better in the morning or the afternoon. I'm open to either of those, and we'll figure that out as we get closer. I just wanted to throw it up there since the syllabus was still in flux on Tuesday. I am. Thank you. This one was a short one.
Good.
So maybe it was still even just allergies that lasted for a couple days. So this is uploaded to Canvas now, both as a PDF and attached to the regular syllabus link. So any other syllabus questions that came up?
No.
All right, let's do some review. If we're going to talk about aromatics and how they show up in the spectra a little bit, so it'd be a good idea to review some of these concepts since we haven't talked about NMR in a little bit. So this is for CH1404. We've got an IR, we've got a proton NMR, we've got a carbon NMR, including one of those Sp2026, which I have all the figures that go with these so we can remember what this one does. So without checking that though, if we can remember that the Sp2026 was the one where it goes up or down based on how many hydrogens are attached to the carbons. And if there's no hydrogens attached, it doesn't show up at all. Right, so where did I put that one? So they're decoupled, all of your carbons show up. Sp90 is less useful because only CHs show up. So if you can use it in conjunction with this other one to be useful, but really this one's more all. You have an even number of hydrogens, it goes downward. Otherwise it goes up. So for this one, that means this one is CH2. This one is a CH2. Where'd my good markers go? I'm out of practice. It's been like 2 whole weeks.
Yeah, it's actually because we like had a happy.
Yeah. All right. So first off, let's go back to our safety blanket. IR is our easiest one, right? We're always looking for OHs, which show up how? How do OH groups show up in an IR? That's okay. I have those ones pulled up too, but you might want to pull. So
In like And they're strong.
They're strong and they're wide. Right, so they show up all the way to the left and they're broad, the round and not sharp.
It's
So that means nothing there means no OH. We've got some peaks here to the right of 3000. Which remember 3000 was one of our big distinctions, right?
right as yes.
That two will show up higher, so left of the line. Sp3 is lower energy, so they show up right. In terms of energy, it's basically, remember we're talking about how these bonds act as springs, right? So that lower energy means more flexible. Higher energy means like a stiffer spring. So we've got only sp3 carbon hydrogen bonds, no hydroxides. Then the other big one that we always look at, and it's labeled for us conveniently, so that's always helpful. That's going to be some form of a carbonyl.
So it's strong around the one. Absolutely.
Yeah, they really show up right around 1700 to 1750. There's a little bit of splitting of hairs we can do. But it can get kind of tricky on that one. And actually I pulled this one up, but I actually don't think I like this one as much as the one you pulled out. Or there's this one. So for a carbon or carbonyls. So aldehydes. It could be an aldehyde. The thing is, these all kind of overlap. We can be pretty sure it's not an amide.
Yeah.
But other than that, these all kind of fit in a pretty similar area. So we've got some sort of carboxylic acid proven probably, but let's check if it's an aldehyde. There's another key that should show up, right?
Because it would have we'd have the OH on the other side.
It would have not an OH, just carbon hydrogen bonds.
Oh, okay.
But the carbon hydrogen bond shows up in its own specific spot. At between 28 and 29, it's kind of weak, but it's kind of all by itself. There's nothing else really around it if you have that. So if we go back, maybe it's not all that distinct though. So we could say maybe aldehyde. But if we look at our formula though, remember that's also really helpful.
Yeah.
We've got 4 oxygens with no OHs.
That's a lot.
It'd be weird to have that many aldehydes in the same molecule. It'd be pretty tricky to do that. It's possible, but it seems more likely that we either have maybe an ester, because that's a carbonyl that doesn't have an OH. Maybe ketone, maybe aldehyde. Let's see. The other nice thing about aldehydes is they should show up really distinctly in proton NMR.
So that doesn't follow the thing we just said that SP3 for bond.
Aldehydes are their own special case because of the oxygen is involved. So when we say sp2 carbon hydrogens, we mean like a carbon, like alkenes or aromatics. So let's see what we can tell based on the NMR regions, because any aldehydes should show up all the way down 9 to 10. And we definitely didn't have anything there. So we really only have 3 signals on the proton NMR, right? And we only have 4 signals in the carbon NMR. So what does that tell us? Bingo. We have a total of 8 carbons, but only 4 distinct carbons. So we've got mirror symmetry somewhere. And especially considering these all have about the same number of hydrogens relative. It's not like we've got 4 identical methyls that are taking up 12 more hydrogens and then 2 others. They're all about the same. So probably we've got an internal mirror plane. We definitely have some amount of symmetry. We've got 4 distinct carbons, one of which doesn't have any hydrogens attached to it.
So it's between the 2 other. Well, single way probably don't, because we all have 4 peaks.
Yes,
Have symmetry.
correct. So what can we say? If we know we've got a CH2 and a CH2, we can put it down. And there's symmetry. So there's really 2 of each of those. How many hydrogens have to be on this last one? 2 times 2 is 4, plus another 4 is 8.
Spaced out.
It means it's either CH or CH3.
So that's 6 more, which means that it could be 2 carbons that are just at the end.
So yeah, so make it a CH3, and then we have 2 of them, right? That gets us to our 14 hydrogens. And 6 of our carbons. So what is this guy down here? Between right around 180, just under 180.
Yes.
Let's check our carbon NMR. It just means that this one's a regular carbon NMR with none of the up and down. That could be the one that has the O's on it. We know we've got a carbonyl, right? Carbonyl probably doesn't have any hydrogen attached to it, not an aldehyde. So that lets us roll out an aldehyde. And means the fact that it's right around 180, this is proton NMR. Let me get the. So between 150 to 200, aldehydes and ketones could be, can't really be ketones, right?
Yeah. I don't think I've ever seen this.
I kind of like this one. I found this in my Dropbox. So this is just for carbon 13s. Aldehydes and ketones would be too far to the left, and we don't think we have either of those. No aldehydes. Ketones would still be a little bit weird because where are their oxygens going? Acids and esters show up right where we're looking in that 180 range. We know it's not an acid though, because why?
Well, isn't it a bit like rearrangement? You know that we're not covering.
Why would it ask you?
Like bases versus acidic.
So I just mean like a carboxylic acid.
Oh. Well, but it. Thank you. That's our CO.
It could be, but what else does a carboxylic acid have to have? A hydrogen attached to what?
The oxygen, and we know we don't have.
And we know we don't have any OHs.
I was thinking of earlier, it's like, instead of.
So-
We don't. Because of this one.
It's the very first thing we looked at.
Oh, yeah, I meant, how do we don't have any single one of. That's in our fingerprint.
Right, we don't know that for sure. If it's an ester, what does an ester look like?
I'm especially remembering this. And so, because I always thought of it of like. Ester, Easter. And hydride, because they all kind of. Yep, that's how I say it. Remember it, they all kind of follow the same pattern.
We definitely have some stuff there, but it's fingerprint, we can't trust it. But this is the only carbonyl group that makes sense based on this. And based on our formula and based on not having any OHs.
And we could,
And we could have two of them.
because that would give all 4 of our O's and our other 2 C's. And
Okay.
keep us in the 2.
So what can we draw that's gonna give us the right formula and the right symmetry that has 2 ester groups in it?
Yeah, because our is line of, yeah, like our mirror would be. So like add another one of the. Oh,
That could conceivably work, right? Or we could put the CH2s on the other side there and have the 2 esters linked back to back. Like,
that is a sport. 6, 7, 8.
you're right. So I could put 2 more carbons in the middle there.
Because we have 2 CH2s.
Yeah.
Or you can put it on the end after the O's. Well, we could see it's like.
Okay, yeah, let me redraw this. Let's look at a couple options. And we'll do this skeletal structure so we can draw all of them on top of each other. One, two, three, 4 distinct carbons. 14 hydrogens, 4 oxygens.
3, 6, 7, 8, 9, 10, 11, 12, 13, 14. I can't submit that today. Or
we could do 2 carbons in the middle.
you forgot the.
Sorry, yep. That meets our same formula. We could take 1 more carbon and put it in the middle.
That wouldn't. But then it wouldn't have our symmetry that.
Sorry, 1 more from each side.
Oh, okay.
So we could have CH3, O, carbonyl, 1, 2, 3, 4.
So that's.
Yeah, 1 more.
Yeah.
And I don't like that I didn't print that the same way on both sides. So we'll do that. Still same formula, right?
So can we look at the like the shielding or yeah?
Yeah. So we can look at the shielding because especially if you look at the. So now that we've got our, it's basically, it's down to 1 of these.
Yeah.
So I'm going to erase the stuff over here. So our carbon NMR doesn't give us a whole lot to go in there, other than maybe if we have an sp3 carbon that directly attached to an oxygen, that shows up in that 40 to 80 region. So that might be helpful, because if we can go back to this one, you say, okay, in that 40 to 80 region, we've got a CH2 that's directly attached to an oxygen, which means that would eliminate this one. Because this would be a CH3 directly attached to an oxygen. And our CH3 is all the way down and fully shielded. We could also start looking at splitting too. We haven't touched the splitting yet. We've got a quartet, a triplet, and a singlet. In our singlet is a CH2. Based on the integration here, right? These are about the same integration, and this one is a little bit bigger. It's hard to tell. But if we got out the ruler, that's, since I'm standing closer, trust me.
Okay.
The singlet being a CH2 means that there's a CH2 group that has no nearest neighbors. Or the nearest neighbors. In the case of symmetry, the nearest neighbors are identical. You can't tell them apart.
Right.
So is there one of these that would give us a singlet on a CH2?
Yeah. That's what I think too.
Yeah. Well, so let's see if the rest of the splitting works there. Because then we get a methyl group with 2 nearest neighbors. That makes sense. And we get a CH2 with 3 nearest neighbors. And the CH2 with 3 nearest neighbors is the most de-shielded. Which makes sense because it would be directly attached to the oxygen.
Yeah.
So all of our evidence is pointing towards this middle one. Because just based on the splitting, this one should have a sextet, 6 with 5 nearest neighbors, definitely not there.
Yeah.
This one's going to have a singlet that's a methyl group. And then this one should give us a triplet. This one should give us also a triplet. We don't see 2 triplets. So just from the splitting allows us to do the rest of this once we get our options written. And then, so that's kind of the way to use the splitting is when if you get the functional groups down using IR, carbon NMR, and write down a couple of options, splitting a lot of times is going to help you decide once you're down to just a few things. We're not going to really look at splitting until we've got it narrowed down.
What is the CMS?
Remember, that's our solvents that we use for the 0 tetramethyl silane. Basically, it helps to have something that we can add to an NMR sample that allows us to set where the 0 is.
Right.
Well, it was a fun little review, right? Haven't done one of those in a little bit.
I always forget.
They can, especially when I just give you a bunch of stuff to go through.
I feel like I like having like all of it versus just like one NMR and one IR to go on. And being like safety as you go up, it's then rounded.
Yeah, be able to nail it down. Yeah, I agree. All right. Let's talk about aromatics. And then we're going to come back and we're going to do another one of those at the end that's specific because we're going to talk about how aromaticity affects carbon and proton NMR specifically. So we're gonna come back into that again later. So the term aromatic, we talked about that a little bit. That's kind of a misnomer. Not everything that is fragrant is aromatic. So in chemistry, we don't use the word aromatic to mean it smells strongly. We would use fragrance. Because aromatic specifically means, well, we'll get to the definition in a second, but it comes from the original definition because the first place they found all these benzene derivatives was in essential oils that smelled really strongly.
Right.
So, and I can't remember all of these off the top of my head. That one's our clove oil. This one is nutmeg. I want to say that's cilantro.
Okay.
And then isobutanol shows up in similar things too. It shows up as a trace product in vanilla. The extra oil, I can't remember which one that one is. Maybe basil. But really, when we're starting to look at what the different use of these molecules are, the reason they show up in all these essential oils is because biological systems use these aromatic components as building blocks. So they're really commonly found in biological systems, which also means one, that our bodies and our senses are trained to or evolved to recognize them. That's why clove oil smells so distinctive. They have a smell receptor site that's shaped like eugenol. And it also means that a lot of active sites in other metabolic processes also have active sites that can be affected by aromatics. So here's these ones. I put both of these in. They're both antacids. But it's interesting because they have a lot of. If you look just at this piece here, that's a fairly specific little chunk, and then a sulfur double bound to an oxygen, and then another aromatic region with a nitrogen as part of it. They're really similar structures, so it makes sense that they would do something similar in the body. So we see this a lot with drug design in pharmaceutical chemistry, where we'll start from something that we know works, and then we'll tweak it to try and either make it better or eliminate side effects. That's basically what they did in the early days of anesthetics. We didn't really know how pain relief worked. So, pre-Civil War, it was basically either knock the person out or give them enough alcohol that they couldn't feel anything.
Right.
But as they started getting better in Civil War and post-Civil War, they started using cocaine because it was really good at absorbing quickly into the bloodstream. And so basically, you would just inject cocaine in the area, and it was really good local anesthetic because it didn't have other local anesthetics. So what they then realized pretty quickly is that that's not good in terms of addiction and like life outcomes. And so what they did is the chemists said, okay, well, what if we chop this cocaine molecule up? And we said, let's take this chunk of it and we're going to give this as a topical anesthetic and see what it does. And they eventually found some combinations that kept the topical anesthetic properties without the high and the addictive properties. And basically anything, this really applies to you in dentistry, but any local anesthetics that end in cane, benzocaine, novocaine, provocaine, they're all lidocaine, those are all derived from cocaine.
Cool. No.
Yes. And so that is kind of the birth of modern biochemistry, was this idea that, there's this naturally occurring compound that has some beneficial effects and some negative effects. How do we maximize the beneficial and minimize the negative?
What gave them that thought of let's inject this straight into the bloodstream to make that? That doesn't just like throw it on.
It does actually.
It does.
Coca leaves. That's actually where it came from. The Incans used to chew coca leaves.
Right.
As in the way that we drink coffee.
Like chocolate?
No, that's cacao.
Oh, okay.
Coca.
I was like, wait a minute. Maybe that's what I like.
Coca is where the word cocaine comes from.
Is there anything else? Plants?
Anything else that comes off of a plant?
The coca plant, yeah.
There's some other stuff that's in there. I think it actually has some caffeine as well as some other things. There's a lot, but this is mainly what it gets used for. You can make it completely synthetically, but first, this was actually one of the first examples of what they called ethnobotany, where they would go and scientists would start looking at traditional remedies from different cultures and start pulling out like, okay, well, what is it about this that makes it work? So they found that the Incans would chew coca leaves and for a burst of energy, and they would, the way that people use chewing tobacco now, they would basically chew it up, stuff it in their cheek, and that would give them energy. So then the chemist said, okay, well, let's see if we can purify that. And they made cocaine.
And instead of the energy, they made a local anesthetic.
They noticed it did both. It's a strong stimulant, but it's also a local anesthetic. So
Eats like sedate and work on it. They try to run around like
right. So that's the trouble with it. It's giving somebody the jitters when you're going to do surgery is less than ideal. But so go ahead.
Bond to the nerves.
The exact mechanism, it does a couple things because it does more than one thing. The stimulant side is it's a strong dopamine releaser. So it's, you've heard about dopamine in terms of like doom scrolling and stuff like that. I'm sure it's a really common way to describe it now. Drugs basically do it just more directly. They basically bond the dopamine to the active sites in the molecules that release dopamine, or they prevent dopamine from being picked up. So if you clog up the way your body clears dopamine, that creates an increase in dopamine in your brain because it can't clear it fast as it would like to. So MAOIs are old school antidepressants. MAOI stands for monoamine oxidase inhibitors, because there's a class of neurotransmitters called the monoamines that are responsible for a lot of our emotion. So dopamine, serotonin, adrenaline are all monoamines, and noradrenaline. And so this MAOI, basically, those would get in the way and cause serotonin and dopamine to build up in your system over time by basically not allowing your body to clear it. Cocaine works differently by causing your body to just flood dopamine, but it doesn't do anything to slow down how it gets rid of it. So what would happen when people abuse cocaine is you flood your brain with dopamine, and then your body clears it right away, and you immediately go and look for another hit of dopamine. So it's a different mechanism. Those are usually the two mechanisms in biochemistry that cause things to happen. It's either you're going to trigger a natural process to release more of something, or you're going to get in the way of breaking it down. This is all very oversimplified because I'm not a neurologist. And I'm wary about talking about neurotransmitters very much anymore because 10 years ago, it was like, oh, serotonin does this, dopamine does this, so adrenaline does that. And it turns out that all of those things are way more complicated than we thought at first. Dopamine's probably the simplest one because it really is just about pleasure and reward. But it also has other stimulating effects like causing your body to have more energy and things like that as well. All that to say.
Sorry.
No, it's okay. I love talking about this stuff. When we're designing drugs, this is a lot of the natural process is we know that this molecule does something in the body. How do we tweak it to either make it more extreme or less extreme?
Yeah.
And some of the first true synthetic drugs that were not based on existing remedies were basically taking some of those neurotransmitters and tweaking them just a little bit. So see if I can draw these from memory. think this is dopamine.
Okay.
One of the first drugs that we ever made, or synthetic drugs, is that. That's the thing. So one of the mechanisms by which we think ADHD is caused is by a lower baseline level of dopamine in the body, in the brain. So people with ADHD, this is the current thinking anyway, is that if you have a lower base level of dopamine in your brain, small tasks that release a little bit of dopamine don't make a big effect. So basically, at least in my experience with my ADHD, maybe it can be different for everybody. I don't like starting a task if I can't finish it. Yeah, that's because all the little steps along the way don't give me a dopamine boost that takes me up above that threshold of feeling like a reward.
Yeah.
A lot of times I have a hard time starting projects if I don't have time to finish the project. Whereas people without ADHD have a higher dopamine level, and so it's easier to stop because you get little boosts of dopamine along the way. I need that big boost of dopamine at the end. So the way that Adderall works and other ADHD treatments, basically boosting the level of dopamine so that it sits closer to the way that neurotypical people have their dopamine levels, so that a small task like turning a page in a book feels the way that might take finishing a chapter for me to normally feel.
Right.
So that's, again, we're still learning a lot about that, but our first modern medication that was not based on an existing molecule, it kind of was based on an existing molecule, was basically, let's take a neurotransmitter and we'll just tweak it a little bit. If you do that, now it's N-methylamphetamine, better known as methamphetamine.
That's what I was gonna ask about.
Yeah, so you just, and there's some stereochemistry in your tube, because now this is a stereo center, and so is this. Actually, I think there's a methyl on. That's what makes the stereo center. But basically, yeah, that's when they realized, okay, well, if amphetamine works, let's tweak it and see if it makes it a little bit more. Methylphenidate, the phenidates look a little bit different than the base structure. They're still the same. I think phenidates have a ring structure here. It might be like a 5-sided ring like that. And so this might be methylphenidate, but I don't remember for sure off the top of my head.
So now that we're talking about all of this, getting my gears turning. So when someone like the drug just plain meth, is it just a methyl group? Like just
No, that's just short for methamphetamine.
oh, okay. Cool. How, because I know it's like really highly like when I on methylphenidate, like I can't get more until like the day it's done because it's really restricted. Because apparently it's really easy to turn into meth.
Well, or just abused on its own. It's a pretty strong stimulant on its own. People that don't have ADHD get a high from it, similar to amphetamine. So amphetamine, just the classic amphetamine, is also Adderall is a recreational drug for people that don't have ADHD as well. So I don't know about methylphenidate being turned into meth. You probably could, but I think more likely people just abuse it the way it is since it's already purified. But all of those, most ADHD medicines are stimulants in some form, which means there's a potential for abuse because they're all stronger than caffeine.
So when people in like high society before we had derived medications from the station, they were just like doing drugs, they were just self-medicating in some cases.
Yeah, in some cases. But where's the line between self-medication and addiction? It starts being hard to draw that line. You've heard the stories of Coca-Cola gets its name from Coke because they used to make a tincture out of coca leaves. So they weren't adding cocaine as a powder to it. They would basically like make a tea from the coca leaves. And so it would have some cocaine in it but it was all about the coca leaves. And to this day, they still use coca leaves in Coca-Cola, but they pull the cocaine out. So you get the flavors without the cocaine. And the other part is actually the cola is actually, there's a nut in Africa called the cola nut, spelled with a K, not a C. The cola nut has some mild stimulants in it as well. So Coca-Cola was basically, you made a tea with coca leaves and cola nut ground up, and then you added a bunch of sugar to it. Yeah, basically, originally.
Yeah, not anymore.
That's why they used to treat it more like it was a medication, like they would call it a tonic. Like anything that you drank that had medicinal value in the 1800s, they called it a tonic.
Yeah.
And a lot of the earliest soft drinks were like that. They weren't really soft drinks. Like 7-Up actually had lithium in it, to mellow your moods. It's a very strong antidepressant that basically like smooths out all of your emotion. You feel nothing. So it was marketed to women. Women got hysterical.
Oh, yes. Yes, too many emotions.
Yeah. So we're just gonna dose them with lithium.
So, but like the word just pull it out is so common to just describe all soda.
There's still a few colas that use cola nut.
Okay.
It's a source of I think that's where the original caffeine came from in Coca-Cola. I think Hanson's, Hanson sodas, they're not as big anymore. They used to be like the original natural soda.
Yeah.
Hanson's cola actually was made from real cola nuts and had a really distinct taste because of it.
Right. Nothing else that we know really.
Right. Yeah. And that's why Pepsi doesn't taste the same as Coca-Cola because Coca-Cola uses coca leaves. They actually get a special exemption from the DEA to import coca leaves and remove the cocaine from it. They sell it to dentists because dentists still use cocaine as a topical anesthetic sometimes because it numbs gums really, really effectively and quickly just by rubbing it on the gum. You don't even have to do an injection. And actually, nose jobs. If somebody gets cosmetic surgery on the nose, they'll actually administer cocaine to the inside of the nose, not by snorting it, but injecting actual cocaine.
And it's here. Coming from the company.
So all that's to say, drug design is really cool, really interesting. It's one of the reasons why biochemistry is so cool. And a ton of these have these these aromatic regions, even if they've got other functional groups as well. You can't really say this one's Zoloft, so that's an antidepressant. This one's here. This one's treatment of asthma. So this is all over the place. We've got antacids, we've got anti-blood treatment or blood thinners. Anticoagulants, yeah. So they administer blood thinners that have these anticoagulants when somebody has a stroke or has blood clot issues. Or just if you have open heart surgery, because they don't want any of those clots in your heart getting anywhere else in your body. And then we're all the way down here to the asthma and antidepressants. Not to mention all the other examples and recreational drugs and neurotransmitters and things like that.
Interesting.
All right, so when we're naming these monosubstituted benzenes, we can just call them benzene. We just stick a prefix on the front. Technically, it's not IUPAC because benzene is not really an IUPAC name, but chlorobenzene kind of fits our rules, right? Nitrobenzene, it's an NO2 group on it. Ethylbenzene, it's an ethyl group on it. A lot of these have common names as well. And these are the common names that are actually more arcane because they're less similar to our IUPAC names. So phenol, we're already aware of.
Yeah.
I meant to mention this when we were talking about MAOIs. This is one of the reasons why it's really important to tell your doctor about all of your medications you're on, because if you have ADHD and you get prescribed something that increases your dopamine levels, and you're also on MAOIs, you can wind up with both of those mechanisms happening at the same time. And so basically what will happen if you do that is your ADHD medication releases extra dopamine and your MAOI gets in the way of your brain clearing the dopamine, and you can wind up not being able to sleep for 3 days. And basically being high for 3 days. So MAOIs don't get prescribed very much anymore because there's a lot of things that tweak your dopamine levels and things like that. We use more like the Sertralines and Zoloft and Prozac and stuff like that.
Yeah.
But see,
It's effective now, but they used it as an antidepressant, so I don't know if it. Well, maybe they were and it's. No, it's, they literally use it as an antidepressant and they also found like a 400 milligram Tylenol. I'm out here on like 15 milligrams to help me with sleep. Yeah, you can mouth that.
so it is antidepressant, but it looks, if they're prescribing it just for help sleeping, then that's going to be not one that you have to be taking on a regular. Like some of them, like Prozac and some of the other classic antidepressants now, you have to be on them continuously for several weeks for them to work as an antidepressant, but they might have other side effects as well. So in this case, for treating of insomnia or anxiety disorders, probably if you're taking methylphenidate, you have trouble sleeping, right?
Well, I've always.
Yeah.
I take methylphenidate and Zoloft. And trazodone is needed, but in the vet, we use trazodone as sedative too. We get like big angry dogs, and now we have this like gabapentin, just like gabapentin and it's like 1/4 gabapentin and 3/4 trazodone, and we're like, we give these 2 of these now, we're breathing in and it calms down for like perfect.
And they do similar things as well. There's a lot of benzodiazepines, things like that in humans, where they'll say like, if you're going to have a minor surgery, they don't want to put you all the way out. They'll have you take a Valium or a Xanax, an hour before you come in, because that settles all your nerves down, and you're not going to be anxious and twitchy. But yeah, so I don't know what the depression is really, really tricky one because we don't really know the mechanism. You think it's tied to serotonin, but that's a correlation, not a causation sort of thing.
I totally don't use trazodone for anything because it is so sweet.
Yeah, that would make sense. They like some of these, they call them tricyclic antidepressants like Prozac and Zoloft, that are slightly different structure, but we don't really know what their mechanisms. We don't know why they work. We just know that in double-blind trials, we see improvement in depression symptoms when we administer them. And it's tied to serotonin levels, but we don't know why. We don't know if serotonin is the causing factor or if it's just a correlated thing. Something deeper is happening that's triggering both the serotonin levels to rise and the depression to lift. So a lot of neurology and neuroscience is a huge area still because we really don't understand the first thing about a lot of these neurotransmitters. And we know the medications work, we don't know why still. Yeah.
They take 30 minutes to get to the first day and like we're in bed. Like 10 minutes later, I'm trying to walk downstairs. This is
Right.
Yes, to go for that. I was so good.
And that's also one of the other things. It's really hard. Everybody's brain chemistry is different, right? And so it's really hard, even day to day.
Right.
So it's really hard to give you like best practices for some of these because it's like, well, for you, because of the meal you had, and it was your first time taking it, it hit you in 10 minutes. But if you had a big meal and you've been taking it 3 times a week for the last month, you might be fine for half an hour. And it's really hard to predict. All right, now that I've made my PSA, talk about drugs a little bit more. Clear those. Phenol, we've seen that one before, right?
Yes.
The rest of these, and some of them like, okay, benzaldehyde, we can figure out what that is based on the name. And same with benzoic acid, they're not technically IV names, but they're pretty close. Aniline and toluene get used a lot. And so those are definitely ones you want to remember. It's a pretty common solvent. We can find it at, you can buy it at a hardware store in Nevada for as a paint thinner.
Yes.
So it shows up all over the place. Anisole shows up in essential oils. Same with acetophenone. I'm not going to tell you don't need to know any of these because they might show up on midterm just as a vocab question essentially.
Okay.
You know where styrene gets used?
Styrofoam.
Yep.
Including the free on top.
Yes. These ones I barely consider common names because it's benzene with chlorine.
So yeah.
Technically it's.
Anisole is like the end with sol. The only thing I can think of in aerosol.
And that's a different root. So I actually don't know where anisole gets its name. Probably from the compound that it came from, where they first isolated it. Anise.
Cool.
And they probably, the fact that it ends in OLE, they probably thought it was an alcohol at first. And then, but it turned out to not be an alcohol.
Okay.
It's OLE is not a common suffix in organic chemistry. We haven't seen that at all yet.
Right.
So that one's one of the trickiest ones to keep. Alcohol would just be OL.
Yeah. So
Yeah.
not related to aerosol.
Not related to aerosol.
Good to know. So it's like maybe you guys have pressure to like make it.
No, at least these ones, at least acetophenone ends in O, and so it's a ketone.
It's not acid.
Styrene ends in ene, so it's an alkene. So to make styrofoam,
Yeah.
it's actually polystyrene, which basically take this and then you do an addition reaction where this gets added to another molecule, which gets added to another molecule. You get one of this big long chain of that has all these benzene rings attached to it. So you basically get carbon, carbon, benzene ring, carbon, carbon, benzene ring, carbon, carbon, benzene ring. So basically this gets repeated indefinitely.
Yeah.
And that, so most polymers have something that looks like that. They're called polymers because you take a bunch of small pieces and you make a big long chunk out of them. It'll be interesting. I actually have a group in Gen Chem this year that's going to try and take styrofoam and turn it back to styrene. They've been watching Niall Red videos on YouTube, and he does one where he takes styrofoam and turns it into red hots.
It's more like.
And yeah, dissolves.
Yeah.
We used to use styrofoam to make napalm, homemade napalm, or actually real napalm, is what they use in Vietnam. They would use it to like firebomb an entire area, defoliate things. They would basically just drop. It burns really, really well and slowly, and you can turn it into an aerosol. So you would basically just blanket the entire area with napalm, and it would just, burn the entire forest down. So basically, this was our way of in Vietnam of negating the advantage that the jungle gave the people that lived there because they knew the jungle.
Yeah.
Is we would basically get rid of the jungle.
No jungle weeds.
Have you ever heard of Agent Orange?
No.
It was a punk band in the 90s too, in the 80s and 90s. Agent Orange was an actual defoliant that actually just killed the trees. It didn't burn, but it killed the trees. But it's responsible for a lot of the long-term health effects that the veterans that came back from Vietnam, and as well as the Vietnamese.
Yeah.
But it was a really big carcinogen and teratogen, which means it caused reproductive issues.
So was it like a poisonous gas type thing?
Basically you would drop it. I think it was a spray. You would spray a whole area, and it was like industrial grade Roundup. All of the greenery would just die.
Well, and like Roundup itself is like kind of lawsuit right now, right?
Kind of, Monsanto's always in a lawsuit related to Roundup. Roundup itself is actually pretty healthy. I mean, like, not like go out and drink it as a supplement, but
You spray it on weeds and like pregnant women are claiming that if they use it while living. Like just from spraying it, like not touching it or anything.
So it's like to get rid of the bugs.
or did it spell
It
that right?
kills the plants. People
So-
like this, you don't have to like dig it up, you just spray it. Hi.
I added an extra syllable in there, glyphosate. So glyphosate is this molecule. The reason that it gets used so much is it only affects broadleaf plants. It doesn't affect grasses. And so you can spray it on your lawn and it'll kill dandelions and it'll kill clover, but it won't kill the grass. It also is pretty harmless to humans.
Okay.
I haven't seen this latest lawsuit, but they've been trying to sue Monsanto for Roundup for 20 years at least.
Okay.
And none of them have ever really, they've won some of them, but they're not state lawsuits. They appeal to the jury in a way that makes the jury find in favor of them, not because the science is actually on their side. Versus Agent Orange kills everything. It's an herbicide and defoliant. Let's see.
Sounds like
Primarily mixture of equal parts.
Yeah.
So organics with trace amounts of this that is a carcinogen. Basically, what these will do is just kill anything with it, any plant, grasses, trees, etc.
But it has aromatic. Which
It does have an aromatic. Exactly. No, that's it. That just kills the plants without burning. Yeah. Correct.
even more soccer just is fine.
Yeah, right.
You're not wrong. I mean, I don't know why they went with that name originally, but yeah,
Is it? I hope so.
it's a good question. I don't actually know.
It better be.
Anyway, so we got down that rabbit hole because we're talking about styrofoam and how it just dissolves. We would dissolve it in gasoline. When I was in high school, it makes for a really good bonfire because it's a really good fire starter. You just take styrofoam. It's really illegal now to burn styrofoam, including turning it into napalm.
So you put stuff in gasoline and then spray the
And-
gasoline on wood.
Yeah, so it basically turns into like a gel. It's like a jelly.
Okay,
So think like the consistency as like a stickier Vaseline.
okay.
And so then you can basically so what they would do in warfare is they would take it and they would just make an aerosol out of it, and then it would just light the air on fire essentially. Yeah.
In which it was stored, it is not the color orange, it is a colorless to light brown liquid.
So
So like most things.
they store it in an orange container.
Yeah.
One of the technical uses of, it's also rainbow heraldics. Okay, so another color name,
There you go.
just because of the color on the start.
Yeah, I mean, I guess when everything's just like brown, but do you form it?
Well, also when you just have to kind of like young soldiers out there,
Yeah, grab the orange one.
you know, like if you grab the wrong one, we're all gonna die. So just put an orange stripe on it.
Right. And then they would just fly helicopters
Yeah.
loaded with this stuff, and they would just spray that stuff like crop dusters, and they would just kill the entire forest, and they would keep everything back from the bases and from the cities so that people couldn't sneak up.
Great.
Yeah. Vietnam was really, really one of the more messed up wars. Other than World War II, Vietnam is up there.
I'm assuming there's.
Because people who bought not worse.
Some of them, yeah,
They're getting.
they're getting up there,
Like, it wasn't like so long ago.
yeah. So there's probably, the advantage of a jungle climate is it having so much rain, and being so close to the ocean, probably most of it has washed off as runoff into the ocean by now.
So,
Right. Yeah,
All of our.
no, that's because the pH of the ocean is changing.
Oh, but it.
I mean, it'd be hard to say. I don't think they used enough that could affect it at a global level,
Yeah.
but that's more about climate change. Because as the temperature goes up in the ocean can dissolve more CO2 into it. And when you dissolve more CO2 into water, you get lower pH because you make carbonic acid. It's a tourist destination now. People love the beaches in Vietnam. All right, let's take our break. We'll come back and we'll talk about aromaticity in 10 minutes.
Are we moving too slow with how many side conversations we're having?
I like having side conversations, so I'm not worried about it. We'll make it up at some point.
All right. That's what I'm saying, like the extra's gonna be something by a car. And then the TVs are gonna have to be in someone's back seat meeting. Or maybe the seat, you have to be someone's back seat. You can both all wear clothes or like box. I got. Okay, cool. And then, don't forget we have to bring everything is. Yes. We still have to wear something. Is that something for each number? Yeah. Well, if we can never have somebody without. Because you have the passes, yeah, according to the break catalog, yeah, and then the other, we were supposed to, and they don't do. Probably would a lot, maybe. You know what, like, you can put stuff in the dress, if it fits. Like, if you show up in the dress, we gotta know what's the dress. Blankets, we like this dress. So we can show the blankets, but we might use this to practice. Maybe. There's some towel that we can find out after that. We can keep most of it off, but I don't think we can. Did you get it? And you really don't move about.
Are you moving again, Taylor?
She's moving out back in plus.
Yeah.
You remember to be overtext in the airport on my way to my.
It actually goes really tight.
After working 2 days in Canada, this city, and now I'm convenient. Start getting my stuff back.
You can do it in a very.
No, and I went to like my events and just like contacts and things. The Monday I came back, so like our spring break Monday, and he was like, "We're gonna be there." I'm gonna cheer about. So I had all come with me. My mom's like, "How long?" Hey, great. Why? Someone tell my see exactly how it is filming everything, and then I took this with my own protection. That says exactly what he needs from me. Exactly. I said, "What about you?" They with me. So we asked him after I tried to get like his birthday text 50%. Okay, I think I checked it. And then the other said, "I stood in my own terms." And then like his first real text is basically with me, and I'm just over it.
Yeah, well, it's kind of
That's
like,
fair.
why can't you do it like now? I'm just like, you threw this on me. I'm in Arizona. Like, I don't know what you expect.
So,
Yeah.
so it was like, as previously stated, as said above.
Yeah.
It was just like these are the consequences of your actions. You made my schedule when you decided to do this. So now you have to live with this. I'll not be responding to him for the text. And he just focused on texting.
Yeah,
Well, now because you stopped texting.
Exactly. And I don't think it's kind of until all my stuff is out of there. The big 65-inch TV, my master's for everything in the kitchen that makes it not a bachelor pad, mine, like the ring camera, like all these things. And he's just gonna come home and be like, "Oh,
yeah.
come back."
Oh, well.
It's a learning experience for everyone, right? That's too bad. I'm sorry to hear about that. But it sounds like it's being handled appropriately on one side anyway.
Yeah. I was really sad. And then he was a dick. It's like, never mind, I've lost that. This isn't even the person I was friends with for 2 years. So we are.
It's disappointing,
It is.
but it sounds like it's for the best in this case.
predominantly Friday and residence class.
Yeah, we're hoping if we can get one more, we were gonna have Autumn, that's but she was a little bit closer to campus.
Mm.
I don't want to pay $1,000 a month independently of rent, so.
404 bedroom.
Yeah.
$1,000.
I was like, that's just crazy, so we already know what building we wanna live in, but we want one more roommate, because I can't just, you know, and she knows it too.
But we did the math,
So. 440 bucks for less
Nice.
parking, which would be
but
great.
we don't know how many parking spots at 3 bedroom comes with, so 1 bedroom ones, there's still like some small, so I have to figure out, but like.
There's parking, you know, you'll be able to find places to park, even if to walk, take turns or something.
Yeah,
So that's nice, because water is expensive.
I guess I can see that, makes
Like,
sense.
I didn't go to expensive ones until like the day we were like testing everything in the apartment, like we hadn't even moved in, there's making sure like cost of time and everything, and it's like, you use always with water, I'm like, it was on for 2 seconds.
yeah, I feel like I turned on.
That's probably a rounding error, like it detected there was some water and it has like a minimum threshold,
Yeah.
but that's still a lot.
Yeah.
But well, that'll be fun though.
I know, it was like we can have like family.
So are you going to UNR next year too? Nice.
Yeah, I was like, then, you know, if we're living in the same place, bring someone home immediately. Get them out of here.
We thought that, like,
It's always hard to tell.
I'm so.
Yeah. Well, he was very confused.
Because he was one.
But anyways,
There's a lot of maturing that happens, especially with boys in the early one. They hit puberty later and longer, and so they're legally considered men, but they don't have fully developed frontal cortexes until like 25.
yeah,
That's a pretty standard thing. Women, it's earlier.
yeah,
So unfortunately, if you date your own age, you're going to be dealing with immature boys for a little bit longer.
Okay. Maybe for the next.
There's one way to do that, yeah. All right. So aromatics in particular are a mess of common names, a mixture of IUPAC with common names. A lot of them. So there's a lot of times we get into there's more than one correct way to name these. For instance, if we had toluene with a methyl group attached to it, we could name that as methyl toluene. Makes sense, right? And we would want to put a number on it. So if this, call this carbon 1, 2, 3, 4, so it'd be 4 methyl toluene. It also has its own common name,
Really?
xylene.
Why? It's not even, where did that come from?
That's the root for wood, and it was first isolated from wood. Sometimes even called xylol, even though it doesn't have an alcohol. I'm not going to use that one because I refuse. But if you go to buy it at the hardware store, it's mixed xylols. It's what it's sold. Xylitol. That's a good question.
And this is that or that. No.
Nothing like this. So also probably because it originally came from wood, because ZY like xylophone. Technically, a xylophone has to be made out of wood, otherwise it's a metallophone.
Oh,
Because xyl means wood, ZYL.
it's from Beechwood.
There you go.
Crystals are so.
They are, huh? It's an artificial sweetener. It gets used in kids' toothpaste because it's not harmful if they swallow it, but it is actually a mild antiseptic or antimicrobial. So it's not as good as fluoride, but it's better for the body if they swallow it.
right,
So I'm not going to have you memorize common names for the dye substituted
okay,
ones. the mono substituted ones, and then we can modify them. So like bromotoluene, nitroanisole, chlorobenzaldehyde.
You go over the orcs of.
Yes. So basically, this is the other way of doing the numbering. Is you're basically saying how close are they to each other.
Okay.
So ortho means that your two substituents are adjacent. Ortho means adjacent. See if I can spell adjacent. I always want to try to put an S, but there's no S adjacent. Meta means once removed.
Okay.
It's actually the same root as when you talk about meta humor. Meta means self-referencing, that it references itself because it's one level removed.
And I'm assuming Mara is twice removed.
Para is twice removed. I always thought it was opposite.
Since we're going to.
So if it's para, they're on opposite sides of the benzene ring. So ortho would be another way of saying 2. Meta would be 3, para is 4. And because it's benzene, and benzene, you can't have more than one thing attached because it's already got 3 bonds to carbon. We're never going to have like 1,1 dichlorobenzene. Can't have that. But because you can't have carbon with 5 bonds.
Right. So
we could call this molecule over here 4-methyltoluene. We could also call it para-xylene. Xylene specifically means that it's dimethylbenzene. You could also call it para-dimethylbenzene.
So we're using this thing like 3 names.
And this is why the aromatics get tricky, is because they were all sort of discovered and isolated before we had IUPAC, and the common names all kind of got set. And they're still there. I wouldn't necessarily expect you to come up with this on the test. But if we built this in MoldView, it'll give us all 3 of these names. Probably what it would consider to be the most IUPAC name would probably be dimethylbenzene. But they're all just as common. And para versus 4, you can use those however you want to. Like I said, if I'm buying it at the hardware store, it's going to be labeled this way. But 4-xylene works too, or 1,4-dimethylbenzene. You just have to remember, if you use the dimethylbenzene, you got to specify what both of them are. Even though it's a ring, so we know one of them is on carbon 1. If you say di, it's got to have 2 numbers.
But you could also just say 4-methyltoluene.
Or you can just say 4-methyltoluene.
I'm not remembering.
Well, you're gonna want to, because we're gonna keep using it. And I like the numbering system more commonly, but we're gonna use these terms when we're talking about these reactions, because when we're gonna find out that the reactions that allow us to put things, attach them to a benzene ring, depending on what's already attached to the benzene ring, will dictate where we add the next thing. So certain things cause an addition reaction to happen at the para position, and sometimes it happens at the meta position, depending on what's attached here first. So we'll use that terminology, but when we go to name things, I'm fine just always using numbers.
So right now I have 4 names for that. I decided 4-methyltoluene, para-dimethylbenzene, 1,4-dimethylbenzene.
Yeah. Okay, it's annoying. Now we've gotten good at the IUPAC name. Why are we changing it all now?
What is that?
The 1,4-dimethyl
I actually don't know. I would probably say 1,4-dimethylbenzene is the actual IUPAC name.
or 1,4-dimethyl.
It would be cyclohexene. Because it would be cyclohexatriene.
Oh, okay.
But we never named benzene that way. Benzene is a fundamental building block enough that benzene is an IUPAC name.
Oh, okay.
Let's do those. So IUPAC name, common name is paraxylene, p-xylene. Like this considers xylene to be an IUPAC name. I don't like that though. So I'm fine calling it 1,4-dimethylbenzene or 4-methyltoluene. The main thing, so remember back when we first learned our IUPAC at the very beginning, we said the most important thing is that our names are unambiguous, that if you know the rules, you can always get to the right structure. A chemist might be like, why don't you just call it xylene? But they're not still gonna be able to draw them all. So that's totally fine. All right. So let's talk about what makes things aromatic in the chemical sense rather than smell. If we look at the energy that we get from hydrogenating alkenes. So cyclohexene is higher in energy than cyclohexane. So this is downhill in energy by 120 kilojoules. The cyclohexadiene winds up being downhill in energy almost double that. Not exactly double that because we do get some resonance here, right? By having them conjugated. So it would stand to reason that cyclohexatriene, we would expect that to drop by about 360, maybe a little bit less because we added extra resonance. But it's actually 152 kilojoules per mole more stable than that. There's actually less energy breaking up benzene's pi bonds than the hexadiene.
And why is it called downhill then?
Because we're going towards what's more stable when we do these reactions. So we should always use up and down to refer to that, because like in physics, when say something that's higher off the ground has more potential energy. So we just use up and down as a way to think about energy.
So like, that one has 100 something more energy than the one on the.
Correct.
And so on.
Yes. So they're all, as these reactions happen, dropping in energy, but benzene, it turns out, it's a lot more stable than we would expect. And this extra 152 kilojoules per mole of stability is way more than we would expect just based on regular resonance. So there's something else going on here. And it turns out we can describe it in terms of orbitals. When we look at the different orbitals we have, when we have conjugated pi bonds, so similar to our dienes from last quarter, we can make different orbital shapes, but the fact that they're in a ring structure means it's not the same as just lining up 6 of these in a row. Like we can still do that, but the fact that they're lined up means that we actually wind up with 2 orbitals that are the same energy. We can add a node here, or we can add a node here and still get the same amount of energy, the same amount of orbital overlap. And that's only because it's a ring where it's conjugated the whole way around the ring. There's no sp3 carbons in the middle to break up the conjugation. And so that actually makes our orbitals more stable. Instead of having it oh, I can add one node here, or I can add two nodes here and here. The fact that we can have them in a ring structure makes it so we can add more nodes and still be stable.
Yeah.
So our shape of our HOMO looks a little bit different than what it would if it was just a straight chain, the way we were used to from last quarter. Right, and then we start getting into the anti-bonding orbitals, and they look kind of similar too. So now we have two nodes, so there's two different ways we can have two nodes in the ring structure and still keep it symmetric. Right, so one of the main things about aromatics is that they have that quality. They have the ability to, they're in a cycle and they're conjugated pi bonds or electrons the whole way around the cycle. Turns out there's a little more to it than that though, because not every conjugated cyclic system is aromatic. They don't all show that additional stability. In fact, sometimes you actually get what's called anti-aromatic, where they're actually less stable than they should be. And it turns out it has to do with the number of possible orbitals. And so when we had, if I go back for a second, we had 6 isolated p orbitals. There was all these different ways we could arrange them. There's basically 6 ways we can line up their phases so that they overlap or don't. And you can kind of see that these energies, if you picture taking this benzene and putting one point of it down, the shape of these energies actually kind of looks like a hexagon. There's 2 that are the same energy that are below halfway. Then there's one that's down here. So if we just connect these, we get a hexagon, right? You can do the same thing anytime you have these conjugated systems, conjugated cyclic systems. You can do something similar. But the difference is, in this case, all of our stable orbitals, all of our bonding orbitals, have 2 electrons in them, right? If we do the same thing with cyclobutadiene, so then it's going to look like, its energies are going to look like this. Well, if we have, so remember the molecule we're looking at here then will look like this.
Yeah.
If we have 2 pairs of electrons in these pi orbitals, right? So 4 electrons total. They'll actually fill up like that instead. So if we have an odd number of electron pairs, we get something really stable like this. But if we get an even number of electron pairs, we get something that looks like this. And the even number of electron pairs, these unpaired electrons, are not stable.
Yeah.
So our criteria for determining whether something is aromatic is it has to be a cycle with conjugated pi bonds the whole way around and an odd number of electron pairs. You need all 3 of those to be true for it to be aromatic. And just because when I took OChem, I totally ignored all the orbital stuff because I thought it was complicated and I didn't want to. Reasonable of a student, maybe not, especially a chem student, but that's what I did. I don't like that though, because I've learned in grad school how important the orbital theory is. I also had really, really old instructors in undergrad that probably didn't know the orbitals that well themselves, if I'm being totally honest, because it's more of a new school way to think about this. You remember Jerry Gubbard? I don't remember how to say his name. He had longer hair and a mustache. He transferred to Davis and he's doing biochem at Davis. And he says that this is the stuff that he knows better than anybody else. That was even the people that were at Davis for their first 2 years.
Yeah.
And what set him apart from everybody else and got him a job in his biochem in a research lab is understanding the orbitals and the entropy and free energy the way we've been talking about it. He just came by on his spring break, which was our finals, to thank his LTCC instructors. And I asked him how prepared he felt. He said that he feels better about all this stuff than the people that have been there for 2 years already. So we're going to keep focusing on this, even though it's a pain.
Yeah.
All right, so here's what the orbital diagram would look like. That's called a frost circle. Well, basically, you have a cyclic conjugated system. You basically draw it balanced on one point. So if we had this molecule, we could draw a molecule like this too. Basically turn it on its side and draw an octagon. So it would look like, let's see what would an octagon look like. It's 8-sided. Except it's not, I can't actually draw an octagon on its side. Take this and you rotate it a little bit.
We needed it once.
Sorry, on a point. But basically you're going to wind up with, instead of having just 4 of these, you're going to wind up with 8 of them, but they're still going to have the same basic shape. And what you're going to wind up with when you add the electrons in, so you're going to wind up with 2 of them. Thank you. There you go. That's why it's hard to,
They're stacked.
because they're stacked. So if I was actually making a look how technical, I'd draw more about the sides, I suppose.
So each of the like little shelves is a carbon.
It's each of the little shelves is an orbital energy, but we can represent it. We're going to wind up with the same number of orbitals as we have carbons in the system.
Okay.
So it's really just a shortcut. It's not like each of these is carbon.
Right.
It's just a way we remember it.
And then the arrow things, the half arrow.
So these are electron pairs, right?
Yeah.
But anytime we wind up with an even number of pi bonds, then that means we're going to have an even number of electrons.
Okay.
And it winds up, we're always going to need even number of pairs of electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Because we're not going to double up in one of these until both of them have 1 electron. Remember that Hund's rule back from Gen Chem?
Yeah.
And this is not stable.
Right.
So we only get aromaticity when we have an odd number of electron pairs. Because if you have an odd number of electron pairs, you wind up with everything staying paradoxically. But with an even number of electron pairs, you get this system.
Yes. And each pair is a pi.
In each pair are the electrons from a pi. Yeah. All right, so this is the way that I think about it. It has to be cyclic, has to be conjugated all the way around with an odd number of electron pairs. The more mathematical way of saying that is there must be 4n plus 2 pi electrons. But 4n plus 2 pi electrons, if you divide everything by 2, that means n plus 1 pairs of electrons, which is another way of saying odd number. So this is just saying the same thing as said here. If it's aromatic, all 3 of these criteria have to be met. So benzene's the most common one. Some of these other ones that are, even the ones that are aromatic, we want to rearrange to make something that looks more like benzene, but we can draw these systems and make these molecules a lot larger. So out of these, which ones are going to be aromatic? Are they all cyclic?
Yeah.
Are they all conjugated the whole way around?
Yes.
So then it's just count number of electrons.
Yeah.
Electron pairs, 1, 2, 3, 4, 5, 6,
That's
even. That is anti-aromatic.
number of bonds in that.
Correct.
I swear I spelled aromatic fine.
It's one of those ones where you repeat it enough times that it's gonna start looking wrong even when it's right.
Yeah.
I did that to myself when I was teaching sig figs in Chem 100 last quarter. I said zeros so many times in a row that I got in my own head. I didn't think I was saying the word zero properly.
Yeah. That has an odd number.
Odd number,
Is aromatic.
aromatic.
I'm gonna have to go look at my final and see if I got my anti-aromatics correct. But
How
yeah,
did you go? You didn't write
no, I know, maybe the
I don't. So we did get through this first lecture before the final last quarter.
Yeah.
that has a good number.
Even number, so it's anti-aromatic.
Okay, that's not so bad. Does this get harder eventually?
So the tricky thing about the anti, so aromatic part is,
Yeah,
where it can get tricky is that not always are you gonna have all of your pi electrons are gonna be part of pi bonds, because
you have a lot.
you have a lone pair, which is conjugated with these. So this still has an odd number of pi electrons, which makes it aromatic. Other than that, aromatic is pretty easy. If you can remember our rules for delocalized electrons, the delocalized electrons still get considered. Because there's 2 pairs of electrons on that oxygen, right?
Yeah,
But only one is present in that resonance. So basically ignore that that one's even there. So we actually laid the groundwork when we talked about resonance, laid the groundwork for aromaticity. Anti-aromatic gets tricky because nothing stays there anti-aromatic, because it's unstable. So what basically happens if you actually have something that's anti-aromatic is either this whole thing rearranges, or at the very least, it'll make it so not everything's conjugated, because it's actually more stable to be non-aromatic than anti-aromatic. And so what will happen is, so non-aromatic just means that it's not aromatic. Anti-aromatic means it's the opposite of aromatic, that it's less stable. In order for it to be aromatic or anti-aromatic, you have to have all of this resonance, right? And resonance can only happen when everything is flat, because you need these pi electrons to overlap with each other, right? So what actually happens in the case of anti-aromatics is basically this whole thing won't stay flat, even though these are all sp2 carbides, they're all trigonal planar in theory. But basically this whole thing like bends in the middle to break that resonance. This is the one time when it's actually stable to be, because the alternative is being anti-aromatic.
Great rests like the bottom viewers. They're reconnected like our houses that we do, like those weird. Well, not houses. Honestly, the paper airplane, because there's so much happening. But they were like this, and then they had the this, like the left.
Oh, like say. Like this? No, no.
But yes, but you add the, when we add.
Yes.
Yeah. Above it's.
Oh, yeah, like the bend out of
it would rearrange, like it would, so that it would become aromatic, it would like us do one of.
It would either break one of these bonds and reform something else. Yeah. It can do something like that, but even at the most basic, what will happen is think about if I put several magnets flat on here, and they're gonna be most stable when they're just laying flat. If I take a really strong magnet and I flip it so that the negative pole is pushing away the other magnets and put it underneath, I could get one of these like bump up and not be flat anymore, right?
Yeah.
That's basically what's happening. It's unstable to stay flat, so it bends.
Yeah.
So basically just tweaks the whole thing a little bit, and that breaks the resonance. It causes it to not be anti-aromatic. It really behaves like it's non-aromatic, but we don't have that full resonance.
So it's no longer, it doesn't become aromatic, it just becomes. It changes from anti-aromatic to non-aromatic.
Right.
It's still considered the same.
Right, and when that's sort of it's no longer that everything's not conjugated. Just like we had to break the conjugation with butadiene, when it was flat, it was conjugated and you could have resonance, but when we rotated it, it would break that resonance. We're breaking the resonance by not letting it stay flat.
Okay.
This is the one time where breaking the resonance makes things more stable. Almost always when you break resonance, that makes things less stable.
Yeah.
Unless it's anti-aromatic. For the purpose of the quiz this weekend, we're not gonna worry about that. I'm just gonna say, okay, just like we did here, it's either anti-aromatic, aromatic, or if we did something like this, so that's a carbon, that's Sp3 carbon now, right? That doesn't meet the cycle, it meets the cycle criteria, but it's not conjugated all the way around. So this would be non-aromatic.
So if it meets the first two but not the third, then it's anti. If it doesn't meet the first two, then it is not.
So here's another example.
It's not safe.
It's not cyclic. It's not aromatic. It's got lots of resonance. It's got an odd number of electron pairs, but it's not cyclic. So this would be non-aromatic as well. Right, and there's the fact that it stays in that cycle allows us to put those nodes in, and that's what makes it aromatic, is the fact that we can add those nodes in multiple ways because it's cyclic. Right, and the way that my very old organic chemistry professor used to say it, he was really a funny guy. I don't think he needed to be funny most of the time, but you said there's just something magical about 6 electrons chasing each other in a circle. Think of them like magical pony unicorns running around a corral. My old OChem, this is one of the ways I help myself pay attention, was we'd write down, his name was Shellhammer, Dr. Shellhammer. And so we'd write down Shellhammerisms on our notes. And so I have a whole notebook full of things that he said.
I used to do that, he would say some random stuff sometimes.
Yeah.
Oh my God, it's so much of my time notes, it's just.
Yeah.
I'd be like, why? Like.
He was the same one.
Yeah, no, it's like this movie or something.
He's Shellhammer was the one who used to who taught us that if you have to choose between tear gas and pepper spray, take the tear gas.
Oh, yeah, but.
Just because it's easier to wash out, it's less intense, doesn't hurt as much. I might have this backwards actually.
No, pepper spray's pretty red, because I
Yeah.
have a friend who, they had to take pepper spray, like she did the military.
Oh,
Yeah.
He's like, I took a shower later, and it ran down my body, and let me tell you, that did not feel good.
Yeah.
The next time. I don't need to know this.
Yes.
To know, I guess.
It's basically
Virgin. Yeah.
the follow-up question was, well, how do you know that? And his answer was, well, my wife went to UC Santa Barbara in the sixties.
Mm.
So he got tear gas and pepper
Yeah.
spray protesting in UC
Yeah.
Santa Barbara in the sixties, so. Vietnam War against. A bunch of hippies. All right. So we got more practice. Aromatic, non-aromatic, or enzyme.
We count one,
We only have one.
so I should look awesome.
That's a personal preference thing. I wouldn't mark you down if you throw through just one for counting purposes.
Do I need to write the whole thing or can I just start in my,
I'm fine with it. There.
so this one is still considered circle,
It's still a circle.
even though there's the extra H. Well,
So remember our rules for delocalize, even though this nitrogen looks like it should be sp3, it's the same as the opposite. Because it's got a lone pair, that lone pair could resonate, so it's gonna act like it's sp2.
that's the hydrogen,
Oh,
but I guess all the carbons have extra hydrogen on these ways.
exactly. So this one, from an orbital standpoint, this is identical to A. It's just, is there hydrogen attached or is there just a lone pair that's not part of the resonance? But as far as counting electron pairs, it's the same. Right here.
Is there an electron pairs on the S?
Yes, same column as oxygen, right? So it's got two lone pairs, just like oxygen would.
And I think or the ends share that double bond that there are.
So nitrogen makes 3 bonds with 1 lone. But remember, each atom can only contribute 1 pair of electrons to the resonance. So the sulfur gets to contribute 1 of its lone pairs. The nitrogen lone pair doesn't get to participate
It's already.
because it's already got a 5 bonds. So there's 3, which makes it odd, and therefore, there you go.
And these ones already have their things contributing, so it's also really odd.
So it's odd, therefore aromatic. Yep.
Yeah. So. As paper. Okay. Positive. So it already gave away its. It has no.
Yeah.
It has no pair because of H plus. So it had a lone pair, just like up here. But we propagated the lone pair, stuck an H plus on it.
So it's 3.
So it's 3,
So it didn't matter.
correct?
Why would you keep that?
Maybe think about it. Set you up for F,
Which is even.
correct? So propagating the lone pair on nitrogen in this case changed it from being aromatic to non-aromatic
To anti.
to non.
Because it's not.
Because we don't have a conjugated cycle the whole way around. By forcing the lone pair to be stuck in a sigma bond, it's no longer able to have resonance. And now it's going to behave like it's sp3. But this one, on the other hand,
It still has,
it still has a lone pair on it.
let me see. I have two questions for Bob. Oh,
This one looks weird, huh?
yes. Three.
It's 3, which makes it.
We had one knot.
We only have 1 knot in this case.
And only two man.
So this slide is more about reminding ourselves of our rules for delocalized electrons and what's considered part of the resonance too. And how does protonating it or having charges affect that. Right, and so this will be your quiz, something like this. It might actually be these same examples, so I might have already done it. I don't remember. Last thing, just because I didn't mention it a second ago. That is our criteria for determining what is considered aromatic versus anti. It's called Kuckel's rule. I had a professor in grad school who was from Poland. And he felt very strongly that Americans pronouncing Eastern European names improperly was a travesty. And this was one of his examples. Don't call it Huckel's rule. He was Polish. His name was Mikkel, M-I-C-H-L. So he said, Huckel. If you call it Huckel's rule, I'm going to fail you.
It's Google.
It's Huckel. The other one is Planck. It's not Planck, it's Planck.
Yes, it is.
Planck's constant, not Planck.
So many people.
There you go. So Joseph Bingle has that on to you.
Oh, goodness.
But this is one of those things that they will throw in a standardized test to confuse you. They'll say, using Google's rule,
Right.
which of these is aromatic? And A, B, C, D.
So really,
It's the same thing we just did.
Yeah.
Conjugated, cyclic, odd number of one.
Yeah, you may have made, right?
But so just don't get confused when they say using Google's rule. It's our same regular criteria.
There is only.
There is only Huckel. Cool. Good first lecture. And we'll talk about reactions on Tuesday. If you submit your tests, you can have yours back. I have it in my office.
I see. You're yours.
I haven't got a position.
I thought I wasn't due till Tuesday.
It's not.
I have a presentation tomorrow. I have this really weird words. Like the whole, no, canine makes displayed the words are just so long and never.
It's like more L's and Y. Like, hello. It's okay. No one's gonna know what you're saying. No, like, I'm so in the back. It'll be like.
If you see Valence wandering around campus today, be sure to notice her hair. She did her own hair today with her alligator clip. Thanks. See ya.